Hi and welcome. We are Team 21086 and today we will be presenting our lunar dust filtration system.
I would now go over the overview of this project. So when man first went to the moon, NASA discovered that the surface of the moon is covered with abrasive electrostatically charged dust. Because of this charge, the dust adheres to surfaces and is found to foul technology and things of that such. And NASA began to study the lunar dust. They created the dust problem. And this was a mission to come up with solutions and technologies that can mitigate this dust and keep it from messing up the technology and getting on spacesuits and into the cabin. Also, the purpose of our project is to create a technology that can mitigate dust in the lunar module. And so we have developed a filtration system that sucks in the air and passes through a multi-stage filtration system to clean the dirty air.
One of the characteristics of lunar regolith is the size variation that it contains. The size variation that the lunar regolith has is 0.5 to 50 microns. To give everyone a visualization, 50 microns is a single strand of hair on our head, and as we go lower to 0.5 microns, it becomes invisible to the naked eye, and we would need the assistance of a microscope. Another characteristics that the lunar regolith has is the shape irregularity. When we compare to dust particles on Earth, we would see spherical shape particles, but lunar regolith inhibits something else containing shapes that have sharp edges to embed itself into suits, into walls, and to equipment. One last characteristics of the lunar regolith is its electric charge. And one of the reasons this is detrimental to the cabin is that the electric charge causes the dust to stick into electrical equipment, causing it to malfunction.
The saline filtration system is a variation on a multi-stage filtration system. It starts off with the air going through a packed bed full of aerogel, and then a baghouse filter, and lastly a series of MERV 16 filters. It ends with a suction fan which is being used to pull the air through the system. There is also an oilless air compressor being used, which will be backflushing the air. By doing this, we will be pulling the dust off of the filters and using the parallel plates underneath to create an electrostatic field which will then be used to capture the dust in the plastic container. This will allow us to preserve the life of the filters and collect more dust. There is a pressure sensor in between each filter. When the pressure gets too high, we know it's time to replace the filters. There will be replacement filters and replacement pack beds built into saline for when they need to be replaced during the mission.
And so now I will talk about the baghouse filter. Our baghouse filter is made of a metal casing and a hollow inside. On the inside of the filter is where you place the pleated filter. And so the idea is air goes in through a intake port, it goes to the pleated filter, and it comes out of the outtake port. And so normal efficiencies of baghouse filters are around 90 to 98% efficiency, and the efficiency of our baghouse filter is 96%.
One of the equipment that we chose for saline are MERV 16 filters. The MERV 16 filters trap dust particle sizes that vary to 0.3 to 10 microns, but it can also trap dust particles that are above 10 microns. But we chose this filter specifically so that it can trap particles that are more for smaller particles such as 0.3 to 10 microns variation. And also we chose this filter because we want to be able to recycle our air in saline so that we are able to filter the dust twice so that when it comes out of saline, we are able to provide a lower dust concentration for the astronauts. Another equipment that we have chosen in saline is pressure sensors. One of the issues that we have encountered through this project is when to replace the filter when it is full, and the airflow efficiency to filter out the lunar dust particles. And one of the solutions that we found is that there is pressure differences between each filter, and it varies depending on what stage it is from. And we've also seen that as pressure increases from one side of the filter, the efficiency of our pump is overcompensating to satisfy the airflow rate that we want it to keep our dust concentration low for astronauts. And this pressure sensor signals astronauts to replace the filter so they can grab our replacement filter during the time of the mission.
Okay, so to simulate this, we created a program in MATLAB that can simulate the dust going through our system. And so what we did is we assumed a concentration, and in the program, we convert this concentration to number of particles, and then we take this number of particles and multiply by the efficiency of the filters. At the end of this, so we get a number of particles coming out, and so we convert that back to concentration. And in this program, we found that our concentration is well below the acceptable OSHA limit of 5 milligrams per meter cube per 8 hours.
And now the environmental and educational impacts of this project. As we saw in the design before, the plastic container will capture the lunar regolith collected from the filter and parallel plates area. This container will remain closed from the start of the mission to the end. With that being said, there is a plan for post-mission operations. This lunar regolith is planned to be given to either NASA or university labs for research. This lunar dust is still an area of discovery, such as studying the charges, studies on mammals, and its long-term impacts on human beings. The idea with this is that there is zero waste from this lunar dust and from this project in general. So using this for research helps accomplish that. And now, finally, the project summary. Through various filtration stages, Selene could be effective in creating a safe cabin and breathable environments. To review the major processes of the systems, they are the packed bed, the backhouse filters, and a series of filters accompanied by an electrostatic field with a collection bin underneath, which is all powered by a pump and can be regenerated. In these 2 semesters, we all worked on our skills and looked to improve as a team. Through honest communication and successful collaboration, this project design became a reality. We had a great time working together and learning content outside of our comfort zone, and we hope you did too. There are a few people who, without them, this project would not be a reality. Thank you to our mentor, Dr. Jordan Hallquist, for meeting and mentoring us throughout this entire process. Thank you to our professors, Dr. Adriana Brush and Dr. Kim Ogden, for being available to us and providing great guidance. Thank you to our viewers for taking the time and attention to watch this presentation. Thank you for getting to know us, but more importantly, thank you for getting to know Selene. Stay safe and healthy.